Hey everyone, welcome to This Explainer. I am absolutely thrilled today because we are going to unpack the literal core of database management systems. Now, if you've been looking at the BCS 501 syllabus, you've probably seen a huge list of terms, right? Schemas, mapping constraints, superkeys, generalization. I know, it can look incredibly intimidating on paper. But today, we're going to break it all down, step by step. We're turning that giant list of jargon into a clear, visual, and honestly, totally fascinating framework. But before we jump into the technical stuff, I want you to consider a question. How does a computer map the messy real world? Seriously, think about it. Our world is full of pure chaos. People, products, orders, relationships, constantly shifting and interacting. Computers, on the other hand, well, they require perfect order. They need absolute logic. So how do we bridge that gap? How do we take the unpredictable reality all around us and translate it into a foundational blueprint that a computer can actually understand and, use to store data efficiently? Well, that translation process is exactly what we are going to cover today. Here is our roadmap. First, blueprinting the digital world. Second, core ER model concepts. Third, navigating mapping constraints. Fourth, unlocking database keys. And fifth, the extended ER model. It's going to be a highly structured, perfectly logical journey through these complex syllabus topics. Section 1, Blueprinting the Digital World. Okay, let's dive into this and see how we actually organize data. To really understand where we're going, we first have to understand where we started. The very first topic in our syllabus addresses this huge evolutionary leap in data storage, the jump from messy file systems to elegant database systems. Imagine an old-school file system, like a room just crammed full of unorganized filing cabinets. It's a total chaos of flat files. You've got a text file for customers, a separate spreadsheet for orders, and a totally different file for inventory. If a customer changes their address, you have to hunt it down and update it in 3 different places, or you risk total data corruption. It is just completely messy. A database system, though, that's an organized, interconnected blueprint. It's centralized. It instinctively understands that a customer is connected to an order, and that order is connected to inventory. It eliminates all that chaos and brings perfect structural harmony. Section 2, Core ER Model Concepts. Let's move on and see how this builds our actual digital city. So, to build this digital city, we rely heavily on the ER diagram, or entity relationship diagram. I want you to think of this abstract syllabus concept exactly like a city planner's master map. I mean, you wouldn't just start pouring concrete and throwing up skyscrapers without a master plan showing where the roads go, where the residential zones are, and how the plumbing connects, right? Well, an ER diagram does exactly that for our database. It's a foundational blueprint tool used to visually represent the logical structure of a database way before we ever write a single line of code. And to build that master plan, we use 3 core elements from the syllabus. First, the data model schema. This is the overarching design of our database, the permanent structural layout. Next, we have instances. These are the actual pieces of data sitting inside that structure at any given moment, kind of like the people temporarily occupying a building. Together, these concepts define the overall database structure. They literally act as the buildings, the roads, and the infrastructure of our interconnected database city.
Section 3, Navigating Mapping Constraints. Now let's look at the zoning laws of our digital environment.
Because obviously a city can't just be a free-for-all, right? We need rules. We need strict zoning laws for our digital world. Enter mapping constraints. These are the strict rules governing how and how many entities can actually connect to one another. If the entities are our buildings, mapping constraints dictate the literal traffic flow between them. They make absolutely sure that our database mathematically reflects the reality of the business rules we're trying to model. And this brilliantly illustrates how these different relational rules work in practice without getting completely bogged down in all the jargon. Let's break it down. 1-to-1, think of a citizen and a passport. One person gets exactly one passport, and that passport belongs to exactly one person. Simple. Then there's 1-to-many or many-to-one. Think about a customer placing orders. One customer can have a bunch of orders, but each of those specific orders, they belong to only that one customer. Finally, many-to-many. Think of students in classes. A single student takes many classes, and a single class contains many students. By explicitly defining these mapping constraints in our ER model, we completely prevent the system from allowing impossible, illogical relationships. Section 4, Unlocking Database Keys. Let's shift our focus to unique street addresses. Okay, so we've got our city built, our traffic laws are firmly in place, but now we've got to talk about identification. We have our entities, but how do we make sure we never ever mix up two identical records? Just imagine going to a coffee shop, ordering a small black coffee, and the database accidentally charges your credit card for the identical order of the person standing right behind you just because you both happen to be named John. No way! That would be a total disaster. We need a foolproof way to uniquely identify every single record in our database.
So we solve this by using a sort of funnel approach. We start really wide and then narrow it down. Right at the top of the funnel is the super key. This is a broad set of one or more attributes that, taken together, uniquely identify a record. So in a student database, a super key could be your student ID. But technically, it could also be your student ID combined with your email address, combined with your shoe size. I mean, as long as that massive combination is guaranteed to be 100% unique to you, it counts as a super key. We're casting the widest possible net for unique identification here. But seriously, nobody wants to use your shoe size to look you up in a system. That's just incredibly inefficient. So we narrow it down. We strip away all those unnecessary attributes from the super key until we're left with the absolute minimum information needed to identify you. That minimal pool, that's called a candidate key. Your student ID is a candidate key. Your unique email address might be another candidate key. And then, from that pool of highly qualified candidates, the database designer selects just one to be the ultimate, chosen champion identifier for that table. That champion is the primary key. It is the absolute anchor of database identification. Section 5, the extended ER model. Because as our city grows, we need some advanced planning tools. As our database city grows and evolves, those basic tools just aren't quite enough anymore. We need more advanced planning tools to handle real-world complexities. The first of these advanced tools is generalization. Think of this as a bottom-up design approach. We look at distinct data points and we find the common ground. For instance, let's say your database has a table for cars and a totally separate table for trucks. Well, they share a lot of attributes, right? They both have license plates, engine types, purchase prices. So instead of modeling them completely separately, we use generalization to extract those common properties and create a broader, high-level entity called vehicle. It makes the entire database significantly more streamlined and elegant. The second tool in the extended ER model is aggregation. Now, I know this can sound a bit tricky, but the concept is actually quite direct. It's simply treating an existing relationship between entities as a single, high-level entity itself. Let's say you have an employee who works on a project. That works on connection, that's a relationship. But what if we need to track what specific tools were checked out for that specific employee working on that specific project? We can't just attach the tool to the employee or to the project. It doesn't make sense. So we use aggregation to literally wrap a box around that entire employee works on project relationship, and we treat that whole interaction as a single new entity. It allows us to build incredible, multi-layered complexity without breaking any of our foundational rules. And that is how the entire syllabus comes together into a seamless stack. Step 1, we start with the base ER model concepts, getting our entities and basic architecture down. Step 2, we enforce order by adding mapping constraints to govern the traffic and keys to guarantee unique identification. And finally, step 3, we handle real-world high-level complexity by applying generalization and aggregation. So what's the big takeaway you should have from all this? Really, it's about the pure ingenuity of database architecture. It transforms real-world chaos into perfectly structured digital blueprints. It takes the messy, unpredictable nature of our everyday lives and uses elegant logic, schemas, constraints, and keys to create a system where data is safe, perfectly searchable, and infinitely useful. I want to leave you with this final, provocative thought. Next time you're buying something online, or booking a flight, or honestly even just scrolling through your social media feed, pause for a second. Can you spot the invisible ER diagram running the system? Can you actually see the one-to-many relationships, the primary keys working behind the scenes to keep your data perfectly separate from someone else's, the generalization of the products you're browsing? Because I promise you, once you understand this blueprint, you start seeing the hidden architecture of the digital world absolutely everywhere. Thank you so much for joining me on this explainer, and keep exploring.